As promised, here are a couple more examples of those induction problems. So here's my proof. We're going to start with our base case. Right? I'll try to give you guys sort of a format. So we'll start. The base case is starting with P of 1. Now, we want to be careful, right? This 1 does not represent, I'm not taking this number and plugging it in on the right hand side. This 1 is representing a sub 1, meaning the first term. And the goal is to get this value, right? That's what it's kind of confusing. On the previous example I did, it was more noticeable because this 1 represents the first term, and my goal is to get this value from the given partial sum formula. So here we have, and I start by just making parentheses everywhere just so we don't make any errors. So I had n on this one and n here. I'm going to be plugging in 1 into that formula, which will simplify to 2 divided by 2, which is equal to 1. And like I said, this one and this one are the same. But this 1 from P of n, from this P of 1, is different. Right? This is the actual value in this first term. This one is the concept of the first term. Right? If I put 2, that means it'd be the second term. If I put 3, it would be in. But the thing is, this problem, it's plugging in 1, looks like the first one, plugging in 2, looks like a second one. But not all of them are like this, right? Like this was the first term, this is the second, this is the third. So I would plug in 2 to try to get 7. I'll plug in 3 to try to get 11. So try to not mix those things up. In part 2, right, this is where I assume. So check on the base case. And then I assume P of K is true. Now, like I said before, that is, so I'm trying to make sure I have enough room for everything. I write it in a different color, but when I say that is, I'm trying to write what does it mean for P of K to be true. I'm essentially just replacing everything with K. Right? 'Cause if I were to say P of K is true, that means I'm just plugging in K into this P of N. So this becomes K, that becomes K, and this becomes K. Right? The idea for this one is I'm saying everything, I checked term 1, and then I check every term after that, but then I need to check that the next one after the, which let's say I checked up to 100, right? You check up to some finite number and it works up to that finite number. But then I want to check, will the following, and K plus 1 is that arbitrary next. So it's the general next term. So that can be at any place in that sequence, right? In that partial sum sequence. The next one is going to work regardless of where you are. That's P of K, right? P of 1 is the first one. P of K is you testing every point, right? The second, the third, fourth, fifth, sixth, seventh. And then PK plus 1 is at the following one. Wherever you stop, that finite check, the next one will also work with P of K plus 1. Now step 3, we must show P of K plus 1, right? Because that's the statement that's in the definition, right? So we check the base case, and then P of K is true. that means P of k plus 1 is true. But that's the part we need to show when you're proving something. That's a definition. But I always like to write out what does it mean to have that k plus 1, right? You can do without this, right? I'm just writing this here that it's a goal for me, right? This is because I'm trying to show P of k plus 1, but the same way I said P of k is true, what does that mean? That means that this is true. But what does it mean for k plus 1 to be true is that this outcome is going to happen. That's what I'm ultimately looking for. So, this is me starting. So I'm going to do 1 plus 2 plus 3 plus k, because that part is true already. That's the part we know. And the idea now is this next one going to be true, right? And that means me putting k plus 1 inside this left-hand side, adding that next term with k plus 1. Not this. I'm not adding this part. This is a part. That's why normally you say you don't have to write this, because this is the ultimate end goal. So I'm only writing as if I added one extra term on the left. But then because of this extra term, I'm going to show that it becomes this right-hand side. Now, this part ends up being the same, because this we know we have that. So that's this. Then we have 1 plus 2, or sorry, this is k times k plus 1 or sorry, I should just write equals here, or arrow, right, all over, or no, nothing, all over 2, no, yeah, right, because I'm using that this is equal to this k times k plus 1 all over 2. Again, we're still adding this k plus 1 term. Before, we were able to do distribution and then things would simplify. But to try to simplify this, at the end of the first video, we showed how to try to combine this a little bit better, because this first term is a fraction. And right now, if I put k plus 1 as a fraction, the denominator would be 1, and then I would multiply by 2, and that's kind of the trick for this one, is multiplying by that 2, because then that lets me write k times k plus 1 over 2 times 2 k plus 1 all over 2. Now, if you see, when you're adding fractions, once your denominators are the same, you can combine this into one single fraction. Now, what makes these confusing really is that there's always this small nuance, and you could probably still, even if you didn't recognize this step, you probably could still right, because I think most people at this step would want to distribute everything, and you can. And then you'd probably notice, just like the previous examples, that you'd end up with some quadratic, and then you can factor it. But if you remember factoring by grouping or factoring by GCF, you notice that there's 2 terms in the numerator, and each one of those terms have identical factors. They both have this k plus 1, k plus 1 in it. So instead of distributing everything and then refactoring, which you can if you want, if I would actually tell you try that if that works better for you. But I recognize I can factor out k plus 1 from this first term and this second term. That leaves me with k plus 2 inside here, right? The idea, I guess I can make a quick note. The idea is, imagine we had 2k plus 4, right? These are two terms that have they have a factor in common. So I can factor out 2 and I'll be left with k plus 1. And that's essentially what I'm doing in this step. Is imagine that this is, I guess, k2 essentially. And then this is another 2 here, meaning it's 4. They both share a factor, so I can factor it out, and I'm left with k plus 2. The same way here, I know 4 is 2 times 2, and 2k is 2 times k, and I'm factoring out one of those 2's, and I'd be left with k plus 2. Right here, it makes sense. We've done things like this before. But all we did here is the factor just got a little bigger. There's 2 terms in the factor minus just one of them. But like I said before, you could have distributed everything out and you could still come to the same conclusion. Now the tricky part is we're still not at our goal, right? But maybe you recognize, oh wait, I have the k plus 1, right? I almost have this k plus 1 in parentheses plus 1. But these parentheses really aren't doing anything. If I were to take them out, I know that this plus 1 and plus 1 would make 2. So if you wanted to look exactly like that format, you could just rewrite this as k plus 1 all over 2. And then, since those parentheses aren't really doing anything, I can just put that part in parentheses. And then that's exactly what k plus 1 is. Right? That's what I just showed. I just showed this is k plus 1. Hence, P of n is true for all natural numbers n. Some people like to finish with a box. Some people like to do these 3 little dots to imply that they're done with their proof. Now, one more example. It could be, this one sometimes it'll be a little trickier, but we can, just trying to show you these aren't all the possible examples, but hopefully seeing a few more is a little more helpful. So we start with our base case, right? That is P of 1. Right, P of 1 is equal to 1 squared times 1 plus 1 squared all over 4, which is going to be 1 times 2 squared over 4, which is going to be 4 over 4, and that's equal to 1, which technically 1 cubed is 1. So if you want to go a step further, I can write 1 as 1 cubed so that it looks exactly like my first term. And that's the overall idea in this problem. Now, so far so good. Step 2, we assume P of k is true. Right, that is, and I'm going to show what that would look like, right, which is it's 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n, sorry, not n, it's k now, cubed is equal to k squared, k plus 1 squared, all over 4. Now, step 3, so put a period there, right? Normally this would be one fluid like sentence, but I'm kind of breaking it up into steps. We must show P of k plus 1, right? Normally I would just say that, stop it, and then write so, but I like to just put what that P of k plus 1 would look like, and it would be like this. So I start by taking 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed plus, and then this is my k plus 1. So I'm saying that there's a next term will give us k squared, k plus 1 squared, all over 4, right? That is, this is equal to that, right? These two are the same. So I'm just replacing that because I assumed it was true, so that means I can use it. And then I'm going to add this next step, right? Which is k plus 1 cubed. And just like the previous one, I can try to get my denominators to be the same. Multiplying 4. That will become, once the denominators are the same, I can actually write this all out as one single fraction. Right? So that would look like this, plus 4k plus 1 cubed, all over 4. Now, distributing all this would get really, really messy. But just like the previous example, if you notice, this is k plus 1 squared. This is k plus 1 cubed. Now, last one, they both were identical because they both were just k plus 1. So they're still the same in the sense of k plus 1, but this one there's 2 and here there's 3. What I'm going to do is factor out one of them. Sorry, 2 of them. Because when I factor out 2, that's going to leave a k squared. Let me move all this up so it gives me more space to work. That leaves me with k plus 1 here. Or sorry, just k squared, because I took 2 of them out. Plus 4 times k plus 1 all over 4. And then I can distribute this 4 in, which just becomes k plus 1 squared. And now if you're wondering why would I think of factoring that out, if you notice, I see a k plus 1 squared here. If this one has 2 and then there's 3, if you remember factoring by GCF, I can at least take out 2. That inside then becomes k squared plus 4k plus 4 all over 4. And then you can, now that that's a quadratic, just like our previous examples, we can choose to factor that k squared plus 4k plus 4, which actually factors into k plus 2 times k plus 2 all over 4. And since those are identical factors, that'll become k squared times k plus 2 squared all over 4. And then that's going to give us almost what we want. If you notice here, that 1 and 1 will make that 2. And if I wanted to look exactly like that, I can rewrite k plus 1 squared, and then that's exactly like p of k plus 1. Now, since I ran out of room, this next part is where I would write pretty much all this. Just gonna copy. All right, this is just how you want to finish your statement right here. So I would just add that portion after this step. So hence p of n is 1 for all, so on and so forth. You could either finish it with the square or those 3 dots. But that's another example. Hopefully this helps.